Previously, we have shown that length minimizing curves of unit speed are geodesics. Naturally, now we want to ask if all geodesics are length minimizing. Do we have this converse? Well, not quite. We don't have a complete converse, but we do have a partial converse. So geodesics turns out to be locally length minimizing. The next few videos will be dedicated to proving this fact, but first we need to explain what does it mean for a curve to be locally length minimizing. Suppose we have a curve gamma on the manifold M, the Riemannian manifold M. Then we say that gamma is locally length minimizing if for every time t0 in here, we can find a neighborhood of t0, a neighborhood u of t0, such that for any pair of points inside this neighborhood, right, so let's say these two pair of points, gamma, the part of gamma lying in there is the length minimizing curve between those 2 points. Note that a length minimizing curve is automatically locally length minimizing. Alright, so that's the definition of a locally length minimizing curve. Now we want to understand why geodesics are locally length minimizing. To this end, we need to recall our exponential map. For a fixed point P in M, let's look at this restriction map of the exponential map. So this is the exponential map restricted to the tangent space to M at P. Remember, this map sends every vector v in this tangent space to the point lying on the maximal geodesic with initial velocity v, right? So the point lying on this corresponding to time t equals to 1. And from that we can deduce that it will send tv, any multiple tv of v, to this point on the same geodesic but corresponding to time t. Remember, we said that this exponential map is going to induce some diffeomorphism between some neighborhood of the origin inside this tangent space and some neighborhood of P. Now, if we take this neighborhood to be a ball centered at the origin, then the corresponding diffeomorphic image here, we call it the geodesic ball. Observe that the image of these radius here are geodesics. We call each such segment inside this geodesic ball, we call this a radial geodesic. The fact that geodesics are locally length minimizing come from the following more concrete proposition. So the claim is that for all point Q in the geodesic ball center at P, the radial geodesic from P to Q is the unique length minimizing curve between P and Q. Alright, so let's see why this statement implies that geodesics are locally length minimizing. And then in the next video, we will prove this proposition. Alright, so suppose that this proposition is true, and now let gamma be a geodesic. We need to show that it's locally length minimizing. So we take a point gamma t0. We need to show that there is a neighborhood W of gamma t0 such that if we take any 2 point P and Q in here, then gamma, or the restriction of gamma to this segment, is the length minimizing curve from P to Q. Okay, so let's first let W be any neighborhood, and then we'll see what we need, and we'll come back and choose it, okay? Let W be any neighborhood and PQ be just any 2 points of gamma lying inside this neighborhood containing gamma t0. Now, we need to show that gamma is the length minimizing segment curve from P to Q. And for this, here is where we're gonna use the proposition about radial geodesic. What we'll do is that we're gonna draw a geodesic ball center at P. Now, as gamma is a geodesic going to P, right? So then this segment of gamma is a radial geodesic lying inside this geodesic ball. So by this proposition, this radial geodesic must be the length minimizing curve from P to Q. And so we see that gamma is locally length minimizing. However, note that here we have made some assumption. How do we know that Q is gonna lie inside some geodesic ball center at P? This boils down to our choice of the neighborhood W. We can choose the neighborhood W to be uniformly normal. That is always possible. And what's a uniformly normal neighborhood? Well, neighborhood W is uniformly normal if there exists a radius delta greater than 0, such that for all point P inside this neighborhood, The geodesic ball, center at P with radius delta, contain W. In particular, if W is a uniformly normal neighborhood, then given any 2 point P, Q, and W, we can always find a geodesic ball center at P containing Q. So in that case, the segment of gamma going from P to Q is just going to be a radial geodesic, and so by our proposition, it must be length minimizing. Okay, but now we need to show that this proposition is true. So why is it that radial geodesics are length minimizing?